here. All right, the basic properties that we need to talk about. The first one is going to be a postulate. So this is a terrible marker. This is postulate 3.1. All right, so postulates. Now, let's talk about what a postulate is before we begin here. Again, it's postulate, P-O-S-T-U-L-A-T. Postulate is a mathematical property. It's some type of axiom in math, something that we take for granted that is so obvious in nature that you cannot prove it. So the basic postulates or axioms in math are like, how I compare this is like, think about like, if you were to try to teach somebody 1 plus 1, right? 1 plus 1, okay? Without, just saying, oh, it's, 1 and 1, and that makes 2 because you're holding up 2 fingers. They have to know the number 2. Like, you have to know what 2 stands for. So you're just adding definitions of words, right? But postulate is something, it's just like that. It's that it's so inherently simple that there's no way to prove it or disprove it. You just have to take it for granted that it just kind of works. Now, this is going to be a tough kind of pill to swallow because when you first see this first property we're going to talk about, you're going to wonder, like, how is that even obvious? I'll explain and how you don't actually, like, prove it in any specific way. So here's what it says. If two parallel lines are cut by a transversal, then, and there's an if out front, by the way. So if two parallel lines are cut by a transversal, then their corresponding angles are congruent. All right, I'll let you write that down. So this is a conditional statement. It's an if-then statement. I forgot to put the word if in the front. If two parallel lines are cut by a transversal, then their corresponding angles are equal. We talked about corresponding angles. That was literally one of the homework assignments you had that's due today at some point by tonight. It's the Google form that I sent out yesterday where you had to look at pictures. And then it would ask you, name a same side interior angle, name a corresponding angle, name an alternate interior, that type of thing. So let's write this one down. We're going to draw it here in a second, but then this is a postulate, right? We don't prove it. We take it for granted. I want to talk about why. So. Okay, so again, two parallel lines are cut by a transversal, then their corresponding angles are equal. So let's talk about this idea. I'm going to just draw a generic drawing of this. So we have two parallel lines. I don't care how you draw them. And we're going to cut it with a transversal. So a transversal is a line that goes through them. Something like this. Again, how they show parallelism, they usually have a little like pink arrow in your textbook. Something looks like this. That shows that the lines are going the same direction, that they are parallel. Maybe this is M and L, and you have your transversals line T. So sometimes in the book they'll kind of have that written off to the side, Line M is parallel to line L, and T is a transversal. All right, so let's discuss this. So we have my parallel lines, we have a transversal. I need to know where the corresponding angles are. So I'll make this line a little bit darker and get some better markers today. All right, so there's your transversal. Okay. What's the definition of corresponding? Let's talk about that. Where would the corresponding angles be? What are the stipulations? There's 3 stipulations for corresponding. What do you guys remember from yesterday? What's one of my stipulations? Where do I put corresponding angles at? And somebody give me one of the rules for corresponding.
Do they have to be on the same side of the transversal?
Yeah, they have to, so the angles you're going to choose are on the one side of the transversal, so either on the right or just the left. You can't mix them. So let's say we pick the right side. Okay, good. That's a good rule. Somebody else now. What's another rule?
One has to be on the inside.
Yeah, one has to be on the inside, one has to be on the outside, right? For the angles. So that's good. So one's interior, one's exterior, and there's one more rule.
They can't be touching each other.
They cannot be touching. So here's the idea. So one's inside, one's outside. They're on the same side of the transversal, and they're not physically touching or adjacent. That's the word that they use. So I'm going to mark this as angle number 1 and angle number 2. Put little numbers there. What this postulate is saying is that those angles are always equal if your lines are parallel. Like, so if I gave you a number, let's say, you know, if I measured that with like a protractor, and you know, I put that little like protractor up there, I kind of measured it, and this turned out to be, you know, 52 degrees. Then the other one is 52 degrees when I measure it. So again, when I measure that angle, that's what the little M stands for. You measure the angle, it turned out to be 52 degrees in that little like mathematical protractor that you have. And that little flimsy piece of plastic. This postulate is something we have to take for granted. You cannot disprove or prove it without just going, well, put your protractor on it and measure it. That's not a proof. It's not proof. It works every time, no matter what your drawing is. And that's the weird thing. It didn't matter that it was 52, it could have been any angle I wanted, but the correspondings will always be equal. It's something we have to take for granted. So again, a postulate is a mathematical statement that we accept as truth. So we accept this as truth without the need of proof. So that's what a postulate is. Okay, questions on this postulate? Okay, I'm only going to do one more property. I was going to do about 2 or 3. I'm going to just do 2 today. The second one, we have to actually prove this. So this next one is an actual theorem. Okay, so I'm going to see if I can move this camera a little bit. You can see a little bit better. All right. Okay, so the next one here. Theorem 3.1. So now we're talking about a theorem. So theorems we have to actually prove. We don't accept these without some proof, some demonstration that it will work every single time. Okay? So there's to prove this one, I'm going to use some properties we talked about since chapter 1, some like a long time ago. So you're gonna have to call back some of your knowledge that we talked about a long time ago. So here's what it says: if 2 parallel lines are cut by a transversal, then
May I have your attention, please? Earlier, the lunch sign-up link was not working. If you were trying earlier to sign up for lunch and were not able to do so, it is now working. So please remember to sign up for lunch at this time. Thank you.
all right, there you go. So you need to do that now. Okay, so if 2 parallel lines are cut by transversal, then their alternate interior angles are equal. So it's got almost the same definition. So now instead of corresponding, we're talking about alternate interior. But we have to prove this, right? It's a theorem. You have to prove theorems. You don't just accept it without proof. And it can't be just something where you say, oh, we'll go measure it. No. A theorem, you don't do that. You have to actually show why. Now, to prove theorems, sometimes you have to use postulates. You have to use previous things we accepted. Or you have to use other definitions of words we've seen previously in other sections. Because maybe that will lead you to the part where, yeah, this is true. Okay. All right, so let's talk about alternate interior. So I'm going to draw this here real quick. So we have two parallel lines cut with a transversal. I'm going to use that same drawing I did over there. So two parallel lines. We'll say these are parallel. Sorry, these look terrible. Okay, so there's my parallel lines. I'm going to cut it with a transversal. Same drawing. Yeah, this green is terrible. Okay, so there we go. Okay, so let's talk about alternate interior. Let's do that definition here. What is an alternate interior? What are my stipulations for alternate interior? What's one of my rules? Please.
They have to be on the inside.
Yep, good point. They have to be interior, right? So I can only pick from like these 4 spots and alternating.
They have to be on opposite sides of the transversal.
Opposite sides of the transversal, one on the right, one on the left. And there's one more stipulation.
They can't touch.
They can't physically touch. So you can't pick like these two. Those would be physically adjacent to each other. I gotta pick so that they're not. So let's say that I'm gonna pick this angle and this angle. Let's say this is 3 and 4. Okay. What this theorem is saying is that angle 3, the measure of it, the measure of angle 3, is congruent to or is equal to the measure of angle 4. This is what I'm trying to prove. This is what we're trying to prove. This is what we're trying to show. Right? Without just going, well, it kind of looks obvious. No, that's not a proof. Obvious is an assumption. Now again, how we prove that one over there, it's like there is no way to disprove this one. Right? That's why it's a postulate. It was an accepted truth. When you put your protractor down, every single time it just works, but there's no other way to show it that it doesn't work, or it does. Like that was the only way. This one, there is a way to prove this. There is a way to prove that these are actually the same digits, no matter what they are. Okay? Now it's gonna require a vocab term. So that's what I'm gonna hopefully kind of fill in for you here. If you guys remember a word that I talked about in chapter 1, it's been a long time ago. This is back in August, September. We talked about the word vertical. Vertical angles, in fact. This is a word, so vertical angles, that's a word that I talked about a long time ago. Okay, what do you remember about vertical angles? I think I used like a pop bottle and a little toy from Hobby Lobby as my example when we did this definition a long time ago. What do you guys remember about vertical angles? If you remember anything about it. Okay, interesting. It's been a while. Okay, vertical angles, if you don't remember, it's when two straight lines cross. When two straight lines cross and you have angles that funnel together. Like they go through a little funnel system and they come out the one ends the exact same angle. So the Hobby Lobby example I use is like two liter pop bottles, like connected at the middle, and you had water in one, and if you spin it, it'll make it like a tornado going down to the pop bottle below it, and it comes out a tornado on the bottom exactly like the opposite. The tornado will be upside down. That was the example I used. Vertical angles, they're equal angles because they flow through the system this direction. That's what we're going to look at tomorrow. We're going to see why these work, but you need to know that. They go across through the little funnel system to the other side, and they're the exact same angle. I'm going to use that fact right here. I'm going to move angle 3 through the funnel system so it comes out over here. Does that make sense? Do you see that? This is also angle number 3. That's a vertical angle. That's something we talked about in chapter 1, a very, very, very long time ago. Now, why I moved angle 3 over, okay, why I moved it through that little funnel system, because I want you to recognize where these are sitting now. Where are those angles currently sitting? What type of angles are they? The ones I put in the little boxes. The corresponding, the thing we just did over there. One's inside, one's outside, and they're on the same side of the transversal and they're not physically touching. We just talked about a little bit ago that corresponding angles are equal. It's something we accepted as truth, right? We can't disprove that. It works every time. Well, by knowing this fact that these corresponding angles are equal and it funnels down, it automatically makes the alternate angles the same. They have to be because of the vertical angle situation. That's something we're going to look at tomorrow. Okay? All right, questions. Okay, that's it for today. I know it's kind of a lot. I'm throwing a lot of stuff at you right now, some properties. We're going to talk about why these things work. I'm going to do kind of a little hands-on activity. We're going to do some physical drawings tomorrow. So kind of be prepared for that. If you have your protractor, that little flimsy piece of plastic where you can measure angles, it'd be a really smart idea if you start bringing that. If you've already lost it, you might want to go get one. Okay? All right, but that's it for today.